Thank you. My name is Yulia, I work on Anoma. I'm going to tell you about heaven. This is the most important part you need to remember. It's going to be about heaven. It's going to be very high level, so like not ZK level, like not precompile level, no arithmetic operations, but we're going to talk about what you can do with ZK and other stuff, privacy preserving technologies. So here's a little bit of context. We're going to be talking about protocols that can be used to develop applications on top of, and at the same time they're distributed systems, so blockchains, right? So examples are Ethereum, Solana, Anoma, and stuff like that. So these are the protocols. When I talk about protocols, this is the protocols. So if we zoom in a little bit, these protocols, we'll see that most of them are transaction-centric. What it means is that it kind of works like this. So there is a user submits a transaction, then goes through ordering, execution, blah, blah, then it settles on the blockchain, and then, someone might say transactions don't grow on trees, but apparently they do. So we have like a garden of transactions, transaction-centric delights. And now we would like to add maybe some privacy. So privacy for settled transactions that are on the blockchain and just exist. So we would like to add some data privacy, meaning that we want to hide the user, we want to hide the data the user submits, and application privacy, because we have applications, right? So what applications the user is actually using. And now you probably wonder, how do we do that? Well, we use ZK for data privacy, and for application privacy, we use more ZK. So a lot of ZK, right? But here are some problems with this. And these are problems I encourage you to work on. First of all, ZK is slow, which is not new, but it's a bigger problem for protocols like I described, because we are building applications. And how do we make applications more private with ZK? We basically make them circuits. So ZK directly limits the complexity of the application you can have on your privacy-preserving chain, right? So the faster ZK is, the more functionality we can have. And at the same time, we kind of want to use ZK VMs because we have a lot of applications, and writing custom circuits for each one might be a bit annoying from the toolchain perspective. But ZK VMs are even slower. So everything is super slow. We need to make everything faster. Precompiles are very cool. But there are more problems. What if we don't want to commit to a single proven system? So yes, BNS might be cool, but what if we want more? What if we want to use Gross16, for example? Could be, right? And so we kind of want to write applications as circuits, but at the same time, we don't really want to kind of specify the field size, the commitment schemes we use. We want them to kind of adapt to what we're building. And this does not really exist right now. So there are just a bunch of proven systems that anyone can use, and they all have different features. But to have a proven system that has two features that no proven system combined before, you have to build your own one, which is not ideal, right? So ideally, you would like to kind of write an application in low-level agnostic way, and then just use whatever ZK proven system that helps with a particular case. So if we do all of this, we imagine that we did all of this, we kind of get into the heaven. Now transactions are powered with ZK, and they're super private. They still grow on trees, but they're very shielded, very private. Everything's cool. And so the next question in our veiled heaven is what we do with these transactions. So I'm a user, and someone sent me something using this system. How do I know about that? It's a difficult question because everything is encrypted, so the only way I can do that is to try decrypt everything. You can imagine it's kind of expensive to do, right? So one approach to deal with that is to ask someone who can help, but they will learn something from it, right? So one of the approaches that you can use is FMD, fuzzy message detection. It's a system that allows detecting transactions without decrypting them. And so basically, this is not exactly optimization like in general. It's more like delegating the work to someone else. And ideally, we would do better. How do we do that is a question for you. So I encourage you to work on that as well. And we can also think about how to prevent detection servers doing some bad things. I also encourage you to do that. And once you do that, we'll have shielded state synchronization powered by FMD or someone else, some horse, that brings transactions from the trees to the user and possibly not back because we have a train. And after that, we already kind of figured out how to deal with transactions, but the thing is that users don't really think in terms of transactions. So it's not like I'm like, I really want this, like, opcode 61. No, I'm like, I want some Bitcoin. And this is an intent. Well, I mean, let's be honest here. I want some Bitcoin. I wouldn't mind. Like, if you want, I can give you an address. You can send me some. But this is my intent. This is super simple. So you probably heard about intents. If not, I'll explain to you what it is. You want something. This is an intent. Luckily, we don't have to formally explain what it is. That would be a bit more complicated. So users think in terms of intents, and transaction-centric protocols do not exactly help with that. So there are a bunch of things that make it difficult because transaction-centric protocols are not designed to work with intents. So what could we do to make it better? We could have an intent-centric protocol that kind of helps to deal with all of these issues, and the user can get back to their intents, right? And so everyone is happy. Well, kind of everyone. I guess someone is not happy in this picture, but don't care about that. How do intent-centric protocols work? So there is a solver. Solver receives intents from users, and solvers matches them into transactions. Here is a problem. Solver sees intents. So we are kind of trying to build something very private, very veiled, and very cool with intents, and like heaven next level. So this.
What's the next level of heaven?
Well, we'll see after that,
Yep.
or maybe not. We're not there yet, so one step at a time. So solver sees intents, right? And we would like to fix that. So we don't want the solver to see intents, so we kind of put a veil on the intents and also add the blindfold just in case. So kind of that's what we want. We want private solving. There are some approaches you can try. So there is a T solver, so like a box, you put intents in there, and then it somehow outputs transactions, right? Also shielded. And there is also like MPC solver that is very unclear how it would work, what it would receive, and all of that. So these approaches kind of could work in theory, but practically speaking, nobody works on that because nobody cares about intents right now. So I encourage you to care about intents. So you can see the diagram is a bit like disintegrated in the middle because what do I draw there? I don't know. So what we really want is something like this. So we kind of send shielded intents to the solver, then there's some magic happens, and then we have shielded transactions output. And you know what to do with this, to be encouraged to work on this, of course. And once we solve this problem, we get to the heaven of veiled intents, where the users submit intents that go through private solving, then produce transactions that are ZK powered. They go through ordering, execution, settlement, they get to the trees, and from there, shielded state sync allows the users to discover what they actually got as a result, because not everything in life is about intent. Someone can send you something like Bitcoins just for free because you gave a cool talk at the Heliax summit. Can happen. So this diagram roughly represents what we are trying to build at Anoma. So now you know, hopefully. And that is actually kind of it. So to reach the heaven of veiled intents, we need to do what? We need the key abstraction layers that abstract the specifics of the proven systems from the application developer. We need more shielded state sync techniques that kind of make it more efficient. We need more private solving techniques that exist. And we would like to have more privacy preserving applications on top of our protocol to reach the heaven of veiled intents. And there are QR codes that are color-coded, and the yellow one leads to our research forum where you can talk to us about all of these problems. You can also follow me somewhere where you will find me, except real life, that is not legal. So if you have questions, I would be happy to answer them. Yes?
Do you already have an approach to sub-private solving?
Kind of. So, there is a very simple approach to solve any problem related to privacy. You take T, you put everything in it, and you kind of start gaslighting yourself that it's fine. So initially, when we looked into these approaches, it seemed okay, but then we did something with T's. Specifically, we did shielded state sync with T's, and it turns out that T's are not exactly ready to be used right now. So another approach would be to use MPCs. MPCs are also very difficult to use because if you want to make something more complex, it becomes extremely expensive. So like imagine you have a bunch of users with a bunch of intents. What does it mean? Does it mean that you have a bunch of MPC agents? Can you imagine how much complexity it will introduce? So these are the two main approaches that we could see. I considered other approaches like FHE, co-snarks and stuff. They do not work directly. Maybe there is some technique that just uses a clever combination of all, but we're not aware of that. That is why I encourage you to work on that with us, possibly. Yes?
When you say T's are not ready, is that a security thing that they leak information if you like?
There are many things. So yeah, security is a problem because so you use like internal keys in the T to protect everything from everything, and there are attacks that leak them, and they're hardware attacks, which means that you cannot fix them yourself, and so you're kind of dependent on the hardware producer, and this takes ages and they will always exist. So this is a big problem, and especially now when they're just not fixed, right? So there are also other issues like T's are not very popular and therefore they're not very accessible. So if you want to use them on remote servers rented from somewhere, you do not have access to low-level instructions that are used sometimes to fix some issues. Another issue is that you do not have tools to use T's, like there are VM-based T's that kind of the idea is that you just load your code in this T and it works. Well, it doesn't work because you need to write like a tiny kernel for it. So, it's like a little bit more complexity than just use your legacy code. And so it's a little bit like complicated right now. I guess a lot of these issues will be fixed over time, but I don't think the fact that you depend on the hardware company will ever go away. So there will always be bugs, and there will always be bugs that depend on the hardware producer, basically. Yes?
I'm curious about the ZK abstraction layer.
Mm-hmm.
Why does it have a QR code? No watermark.
Oh, well, you can create one. There is no QR code because this is something that becomes more of a problem for us right now, and I don't think we're gonna work on that, to be honest, because I don't even know how to address this. It just seems like it takes a bit more resources than like 3 people kind of like trying to make something work using ZK, MPC, FHE, everything to build the heaven. So that's your job. I can tell you what app I used to create QR codes just to make the job easier. Just a Python QR code library. Pretty simple to use. Yes. So yes.
It's not a question, but I want to tell you that the FMD horse is my favorite.
Oh, thank you. Thank you.
But actually, I do have a question.
Yes.
A very, very basic one. T and MPC, what do they stand for?
Oh, right. So T is a trusted execution environment. It's just a hardware tool that kind of does protected computations. It's protected with a key issued by the hardware company like Intel, AMD, or whatever. And MPC is multi-party computation. So basically the idea is that there are a bunch of people knowing something, and they perform computations on what they know, computing together the result of something without seeing what the other people have. So this is the two things. Yes?
Do you have an estimate for the size of these solver circuits potentially? Or you say it's complex, but how complex really?
A solver, like MPC circuit, or
intent solvers.
When you talk about like circuit, what do you mean? Or like application circuit, or solver like computational complexity? Because solvers do not run circuits. I mean, they create proofs and they verify proofs, but they do not have like circuits attached to them. So what do you?
There's like a solver algorithm, right? To match an intent So
Yeah.
this specific algorithm.
Yeah, it's very complicated. So generally, like it's so complicated, you cannot solve it in the general case because it's like a bit of outside of NP world. Solvers would be very hard-working entities that are designed to work with a single-ish problem at once. All I can say right now is that it's like going to be complicated. So just to imagine, right? Imagine we have like a very simple exchange, right? So I produce a lot of intents, like I want to exchange my Bitcoin for Ethereum that I received from you, of course. And then you produce a bunch of intents like that. And so the solver sees all of them and they have to go through them, like match them together because they're also not so, like trivial. They're not just like, I want this for that. It's like there is an exchange rate. There are maybe some other conditions that are related. So yeah, it's going to be expensive, very expensive. Yeah. We kind of like take all of the costs and put them on solvers. So this is how it works roughly. Yeah. So I guess there are no other questions.
Yeah, I think we're good. Thank you so much.
Thank you.